Hello and good morning, afternoon, or evening. Who knows anymore? Um, this is part two of this sort of selected chemistry section of the course, talking about Grignard and organolithium reagents. These are extremely important because they provide a way to make carbon-carbon bonds. So as we know, organic molecules are mostly made up of carbon frameworks. Um, and this adds larger carbon groups. Notice up to now we were only able to add a single carbon via the nitrile group from HCN as a nucleophile. This broadly falls under the topic of organometallic chemistry, a very large subfield of organic chemistry, especially organic synthesis. You won't see any syntheses nowadays that don't largely use organometallic chemistry. Grignard reagents, discovered by Victor Grignard, actually. He won the Nobel Prize for that, I want to say 1912 or somewhere around there. They're made from magnesium metal. And it's really interesting because the metal inserts in the bond between carbon and a halogen, showing bromine here, but it could be chlorine. This will create a Grignard reagent. This Grignard reagent, if we examine this bond more closely, really there's sort of a push of electron density in the direction of the carbon. So it behaves very much like a carbon nucleophile. Notice this carbon, almost a carbanion there. So extremely useful. You can even insert the metal, as we see here, into the bond between a phenyl group and a bromine, leading to a phenyl anion, like a benzene anion that can actually act as a nucleophile to form a new bond. And if you don't believe me, here's pictures from our very own Organic 3, well, I guess it's Organic 2 lab that goes along in third quarter. And what we see here is the metal. There's the magnesium metal stirring with this compound, and eventually you can see the metal literally dissolving, and there's our phenyl magnesium bromide product that we then use to as a nucleophile to bond to other materials. Now there's a really similar set of reagents using lithium, and we call them organolithium reagents. They don't have a personal name to them. Also created from alkyl halides, mixed with lithium, a little bit different, more of an exchange. So each part of the alkyl halide gets bonded to a lithium, if you notice. But this is the one we're using, the alkyl lithium. Very similar, behaves like a carbon nucleophile. Check it out there. And you can do the same thing. You can have it creating a phenylithium as a nucleophile. So when we're using these reagents, we would draw them as reacting in this way. See the arrow here? Basically same kind of arrow pushing. Maybe not quite what really happens, but it's for all intents and purposes what does happen. The carbon group comes along with these electrons. This part is lost, but basically they behave the same way, forming a new bond using these electrons, like as if it's a carbon nucleophile. So some specific examples. For example, here's our methyl magnesium bromide Grignard reagent attacking this carbonyl. So we're kind of picking up where we left off with addition of nucleophiles to carbonyl groups, and it's going to push electrons up. Don't forget this carbonyl is polarized. So there's inductive effects as well. Everything's due to structure and bonding. That carbon nucleophile ends up forming this new bond here. The second step, you'll often see addition of water, sometimes a mild acid, H3O+, in order to protonate the oxygen because, right, we're going to shoot electrons up here. There'll be an extra lone pair. It'll have an oxygen with a minus charge. And then that minus charged oxygen can be protonated in step 2. So you'll always see that step 2. Addition of water. A lot of times synthetic organic chemists will call it we're quenching the reaction with water. Organolithium reagents can do exactly the same thing. Push those electrons up. You can sort of even abbreviate those electrons, then can pick up a proton from there and so forth. But you have this new bond forming, delivery of the carbon nucleophile there. Here's one more example. Phenyl magnesium bromide, addition to this carbonyl group, pushing electrons up, protonation, forming of this new carbon-carbon bond. So we can add large carbon groups now. What do I need to point out that I haven't pointed out yet? Of course, every one of these products creates a chiral center, a chiral carbon. And so remember, addition to carbonyls, as we saw, I believe, in our very last video, this bond-forming reaction can take place, any of these can take place on either face of the carbonyl group. If we look down here, messing things up here. But in every case, then, you can have addition on both, you will have addition on both faces of the molecule. So, in fact, this product would look like this. And then you would also have this product in equal amounts, most likely. And remember, you have to draw the wedges and the hash marks to indicate which ones of these are which. And we can easily assign RS configuration, priority groups 1, 2, 3, 4. As we're looking at it, however, 4 is in the plane, so it gets a little bit tricky then in this case. As I'm looking at it, it appears to me like it is S configuration there. And now we have priority groups 1, 2, 3, 4. And it appears to me that we are looking at R configuration there. So, you know, the foolproof way is to build models, assign each priority group, and then assign each 1, 2, 3, 4 to, or 1, 2, and 3 especially, to the different colored groups on your molecule, on your molecular models. Have 2 of them, an R model and an S model, and then you can easily point 4 away from you. Okay, so in your reading and in your homeworks, you may also see that these reagents, if they're used with esters, like we see here, can add twice in succession. Check it out. You can make an alcohol, a tertiary alcohol, with 3 identical groups if you want to, because notice we're adding this identical group to what's on here already. So we're actually just going to explore that chemistry later. So, but I know you're going to encounter it in your reading. The Klein reading is a little bit better, I think, in this case, and problems there. There's some in McMurray too. McMurray doesn't talk about organolithium reagents. Actually, neither of these talk about organolithium reagents very much, but in fact, they have supplanted Grignard reagents much more. They are higher yielding and faster rates of reactions, actually. So it's a little bit strange that the textbooks don't cover that. So there's also going to be a worksheet coming up on this too. All right, have at it.